Yeah, for the next hour or so, I'll tell you about some of the things that we've learned from gravitational wave observations of stellar mass binary black holes. So the sources that I'll be talking about are like what you see here in this movie, where you have these two black holes in a binary system and they're orbiting around each other, and they're close enough together that the orbital evolution is driven by this gravitational radiation. So these gravitational waves propagate out from the binary and travel across the universe until they reach us here on Earth. And amazingly, we have these extremely sensitive detectors that are able to detect these tiny ripples in space-time. So we have a worldwide network of these gravitational wave observatories, the two LIGO detectors in the US, the Virgo detector in Italy, Kagra in Japan, and then LIGO India, which will come online around 2030. And so we've observed for a few observing runs so far and are currently in the middle of our fourth observing run. So you can see here as time goes on in the advanced detector era of LIGO turned on in 2015 for the first observing run. Then there was a second observing run a couple years later. The most recent observing run that we finished is the third observing run. So I'll be talking about the sources that we've detected in these first three observing runs. We are currently in the middle of this fourth observing run right now, but we don't have any public results from that yet. And yeah, the numbers up here just refer to our sort of measure of our sensitivity to binary neutron star sources. So the main thing to note is that the numbers do go up with a different observing run. And so that leads to our increasing detection rate as a function of different observing runs, because the detectors are more sensitive, so they're able to probe bigger volumes of the universe and catch further away gravitational wave sources. And so you can see here, as a function of time that we've been observing the cumulative detection rate, this plot does include the public alerts from the first half of the fourth observing run. And so you can see that this curve steepens with time as the detectors become more sensitive. And we have close to 100 events at the end of the third observing run, which is what I'll be talking about, and almost doubled that sample in the fourth observing run so far. Great, so we have a bunch of these gravitational wave sources, and again, each one of these sources consists of two compact objects, mostly black holes, but also some neutron stars. And this plot that we love to shows the masses of those compact objects. So each gravitational wave source is represented by one of these arrows, and we have, in this case, two black holes with their masses shown on the y-axis. So around 20 solar masses, around 30 solar masses, and they merge and make a black hole that's around 50 solar masses. And you can see the neutron star sources down here. There's a few of them. They are super exciting, but I'll be focusing on the black holes because we have so many of them. And there's a lot to learn from the population of black holes. So some of the things we can learn is how are black holes made, for example. So we know that one way our universe makes stellar mass black holes is through the evolution of massive stars. So when massive stars, so stars around 10 solar masses or heavier, end their lives, depending on their initial metallicity, they can end up as a black hole or a neutron star. And this is kind of a simplified diagram of how that happens. We're not exactly sure, how these massive stars live and die And so that's one of the things that we hope to learn by actually observing all of these black holes and neutron stars in the stellar graveyard. The other thing that we want to learn is how do you actually get two black holes to end up in a binary that's tight enough to merge through gravitational radiation within the age of the universe. And this is a non-trivial problem because gravitational radiation is very inefficient. So you have to have your two black holes quite close together in order for them to have any chance of merging within the age of the universe through gravitational radiation. So there's a whole suite of proposed processes by which you can get this to happen. We kind of think about it in terms of two broad channels. It's really more like a spectrum between isolated and dynamical channels. But in the limit of very isolated binary evolution, you have two stars that start off in a binary and then they live their life and a bunch of stuff happens. And ultimately you can get two black holes if you're very lucky, are close enough together that they can merge within a Hubble time. And then all the way on the other end, you can have like things in the middle, like triples, or, when you have like 5 stars. But in the limit of having a bunch of stars, you can end up with a bunch of black holes, and then the dynamics takes over and you have a bunch of dynamical interactions, things like exchanging partners and various dynamical assemblies that can get you into a tight binary of black holes. And one thing that I'll come back to later, which you can see in this cartoon by Shanika, is that in this scenario, when you have a lot of dynamics, you have a lot of exchanges, the spin tilts, for example, tend to randomize, whereas in the limit of very isolated binary evolution, you have spins that might be preferentially aligned because those black holes have spent their whole lives together and really affected each other.
And the subsequent radiation doesn't process them into the same state?
Yes.
This captures them to some place where they then radiate for close to a Hubble time?
Yes. Yes. So they do process. That's absolutely correct. If you have a completely isotropic spin tilt distribution and then you go through gravitational radiation and precession, they'll stay isotropic.
It doesn't preferentially radiate at any differences, is what you're saying.
Yeah, but if you start in like various like close to aligned with some, then you can get precession doing weird things, and there's like spin orbit resonances and stuff. I know like BJ, who's sitting behind you, has written some stuff about that. Yeah, but isotropic stays isotropic, so that's handy. Okay, and then kind of zooming out, these binary black holes are merging in the universe, right? Inside galaxies, probably. I mean, maybe not, but probably inside galaxies. And so that's a really handy way that we're now getting access to learning about things like galaxies, the evolution of galaxies, large-scale structure. And also, I won't talk about this today, but another really cool thing that you can use gravitational wave sources for is measuring the expansion history of the universe, because we get the luminosity distance of the binaries directly from the gravitational wave signal, but I won't talk about that today. Okay, so we want to learn all these things from observing binary black holes. Fortunately, binary black holes, well, both fortunately and unfortunately, they're extremely simple objects, and we get a lot of information from the gravitational wave signal. So first, we can learn how big is each black hole in the binary. So this, to first order, is the most important thing. It affects the frequency evolution of the gravitational waves. the more massive the black holes, the lower frequency the gravitational radiation. And so we refer to M1 as the primary, just the most massive black hole in the binary, and then there's M2, which is the less massive black hole. Then there's also some information about how fast they're spinning, and then where are those spin axes pointing relative to the orbital angular momentum axis and also relative to each other. And then we can also learn a bit about how far away the merger happened. So as I said before, we learned the luminosity distance to the source. And for the rest of this talk, I'm going to assume that we know cosmology perfectly. And so we just convert luminosity distance to things like redshift and look back time, and things like that. And then we also learn a bit about where the source happened in the sky, but that's not very good. Our localization isn't very good yet, so I won't really use that information. And then in order to really learn about astrophysics, we have to look at all of our sources and analyze them as an astrophysical population. And so we get all these mass measurements and spin measurements of the individual sources from their gravitational wave signal. And then we want to combine those into a population distribution. So we introduce a population model that describes things like the mass distribution of binary black holes, or the rate, the merger rate as a function of the black hole primary mass. And so the simplest example is we can fit a power law to the black hole masses and just model this rate as a function of mass with some minimum mass, some power law slope, and some maximum mass. And now we aren't necessarily concerned with what's the mass of an individual event is, but with what the minimum mass, the power law slope, and the maximum mass of a population is. So we get these measurements of the population level parameters. And to do that, we have to take into account the measurement uncertainty of those individual events, like the fact that we never measure the mass of a black hole perfectly well. We have some posterior distributions on black hole masses that have like very particular shapes. They're not like simple Gaussians or anything. And we also have to take into account selection effects. So the fact that some black holes are easier to detect because they're more massive, for example, than other black holes, and that black holes that are closer by are easier to detect because their gravitational wave signals are louder. And just one plug here, you should be careful about writing down your hierarchical Bayesian likelihood, and don't just fit the detected distribution. It can be tempting to do that, but you shouldn't. And if you want to know why, you can read this paper or ask me later. Yeah, so one example of selection effects, and this is the most important selection effect that we have to deal with, is the fact that the massive black holes are overrepresented in our sample because they're easier to detect. So the sensitive volume increases very strongly with the total mass of the binary. The different colors here are just different mass ratios. So this is an important thing that we take into account. And so all the like population distributions that I'm going to show you are the astrophysical distributions that kind of undo this preference for more massive black holes. And there's some other preferences with respect to spins and things like that. It's really cool that we can actually measure this well for gravitational waves. I think that is one thing that makes gravitational waves so awesome for astrophysics, is that they're an astrophysical source where we can actually characterize our selection effects, because we know what gravitational waveforms look like, not perfectly, but a lot better than, modeling like X-rays from weird systems that we maybe haven't seen before. So I think this is pretty useful. Okay, so, oh, yes.
Can you please turn on your mic, please?
You were saying that the we tend to see the more massive black holes because they're louder.
Yeah.
As a person who doesn't do black holes, very naive question, but are the massive black holes also lesser? So within, assuming that they are within the sensitivity limit, the sensitivity cap, shouldn't the two things compensate because the smaller black holes are also more frequent, so to say, the mergers of the smaller ones?
Yes. So basically, what this plot is telling you, so roughly the sensitive volume increases with a power law as a function of total mass. And so the power law slope is roughly 2.2. So if the underlying black hole mass distribution was a power law with slope negative 2.2, then our detected distribution would be roughly flat across masses. So you'd need something that's steeper than negative 2.2 in order to get more small black holes detected in the sample. Yeah. Okay, yeah, so for the next half hour or so, I'll cover some of the astrophysical lessons that we've learned from our current sample of binary black hole mergers. The first one I'll talk about is formation environments, and can we learn something about globular clusters from binary black hole mergers? Okay, and why globular clusters? Well, I showed this picture before where we have these different physical processes in different environments where it has been proposed that binary black holes can assemble and merge. And so if you think about the dynamical channel, that is basically anything where you have a dense cluster collection of black holes. And one common place we have a lot of these in the galaxy where this can happen is inside globular clusters. And there are other environments, but I'm going to focus on globular clusters here because I have worked on that. So one way that we can distinguish this isolated channel from this dynamics channel, and again, I'm using very simplified language here. It's really like a knob that you can turn between isolated and dynamics. But one way that you can distinguish these two extremes is by looking at the statistics of the spin orientations. And so I'm going to use this one specific spin parameter, which describes the spin in a binary black hole system, which is the mass-weighted spin along the orbital angular momentum axis. This is known as chi-effective, or the effective inspiral spin. And it's basically, you have your two black holes in your binary. They have some spins and some spin orientations, and you just take the component of each black hole's spin that's projected along the orbital angular momentum axis, L, and then weight that by the mass of the black hole and take the mass-weighted average of that, and that's your chi-effective. So we can do this for every individual black hole. The reason that we like to use this parameter is, one, it is approximately conserved during the inspiral, so we don't have to worry about this like precession thing. And also it affects the frequency evolution of the gravitational wave signal, and so it's the best measured spin parameter, or at least one of the best measured spin parameters. Okay, so just a couple of things that we can learn from the chi-effective distribution. One, if we have negative chi-effective systems in our sample, then that implies that at least one of the spins is tilted by more than 90 degrees. And that is easier to accomplish from dynamical assembly, where the two black holes don't know anything about each other's spins. That doesn't really affect how likely they are to partner with each other, versus an isolated binary evolution where there's a lot of processes that tend to align the spins of the stars, and that affects the spins of the black holes, et cetera. And then the other thing to note is that isotropically oriented spins, which is what you'd expect if the spins are just completely random in the limit of a very dense environment where there are many exchanges that tend to randomize the spins, that would imply that the chi-effective distribution is centered at 0 because half the time it's preferentially positive and half the time it's negative. So we can actually measure the population distribution of chi-effective from our latest catalog of gravitational wave sources. And what is shown here is that cumulative distribution that we infer as a function of chi-effective. And these are just two different, like very simple models that we fit to this distribution. So for example, the Gaussian model is literally just fit like what the mean chi-effective is and what the standard deviation of the chi-effective distribution is. And what we learn from this population analysis is that some black holes have tilts that are larger than 90 degrees because there is a small but non-zero tail of chi-effective towards negative values. But we also learned that the spin orientations are not isotropic because if you look at the median or chi-effective, so where the 50th percentile here is, it is positive. So it's not, if the spin orientations were isotropic, the distribution would go through this point here. But there are a majority of systems have chi-effective greater than 0. So what this implies is that the dynamical environment that I'm focused on, which is globular clusters, may have produced some, but not all black hole mergers. So they may have produced this tail towards negative chi-effective, but not all of the black hole mergers come from clusters because the spin orientations are not isotropic. So we can take this a step further and actually try to infer what the rate of systems with isotropic spins is as a function of redshift. So we can start by just measuring the total rate of binary black holes as a function of redshift, and that's what's shown here in orange. So that's just the total rate of binary black holes from redshift 0 to redshift 1, which is up to where we could detect gravitational wave sources in the third observing run. And then we can, look at this. We can fit a distribution like this that might evolve with redshift, and we can look at what fraction of binary black holes have negative chi-effective as a function of redshift, and then multiply the orange curve by that fraction and get this blue curve here, which is the fraction, which is the rate of binary black holes that are consistent with having isotropic spins as a function of redshift. And so you can see that the blue is always below the orange because that fraction is not 1. And it also has much larger error bars because we now have to also measure the spin distribution, and there's uncertainties around that. Yes.
Can I ask, how does the isotropic, you're using somehow that cumulative distribution you showed before.
Yeah.
To put some upper limit on how much isotropic things you can fit into that distribution.
Yeah.
And what is the isotropic distribution look like?
Yes.
In Kaya, like what does isotropic mean?
Yeah. So
not uniform in Kaya.
Yeah. So isotropic just means half of your systems have negative chi-effective is what I'm using. So the fraction that is consistent with isotropic is the fraction with negative chi-effective times 2.
Right.
So if it was 50%, it would be 1, but if it was 20%, it would be 40%.
Okay.
Yeah. Yeah. Okay. So now for the next couple of slides, I'm just going to assume that this blue rate here is a measurement of the rate of binary black hole mergers that originated from globular clusters. In reality, it is an upper limit on the merger rate from globular clusters, but we'll just see how far we can get, assuming that it's the upper limit is the rate. Okay, and so we can use that rate of binary black hole mergers to actually probe the properties of globular clusters. Here's a globular cluster. So basically, what we do is we can take simulations of globular clusters. And so this is from this catalog of simulations led by Kyle Kramer that uses the Cluster Monte Carlo or CMC code. And what this catalog is it tells you for different masses of your globular cluster and for a different virial radius of your globular cluster. So this virial radius here is in parsecs. So this is the densest clusters up here, down to more diffuse clusters. Starting off with those total masses and those virial radius, and also the metallicity of your cluster and where it is in a galaxy, they've simulated how many binary black hole mergers you get out of that cluster. So the number of binary black hole mergers that you get from a given cluster is very much dependent on the mass of that cluster and its radius, so like the density of your cluster, and also things like the metallicity of the cluster. And so, right, in particular, the most massive, densest clusters up here predict the most number of binary black holes. And so we can compare the rate of binary black hole mergers to what different mass distributions of globular clusters would predict, for example. So like the relative number of small globular clusters compared to big globular clusters would predict a different rate of binary black hole mergers. And so we can infer the globular cluster mass distribution by comparing that to the rate that we've measured of binary black hole mergers that we've said come from clusters based on the spins of those binary black holes. And so here's like the fit that we've done to the mass distribution, and that is consistent with the typically assumed Schechter function for globular cluster masses, where you have a slope power law with slope of around -2 here, and then your Schechter mass at around 6 point something, then your exponential fall off. Yes.
At z equals 0, I think of the globular cluster distribution as like the Gaussian around 10⁵,
yeah.
10⁶. But
yes.
at z equals 2, we're assuming that,
so,
they haven't been destroyed yet or something.
Yeah, so this is the initial masses of the globular clusters. And yeah, at the time of globular cluster formation. So the assumption is like the globular clusters we see today in the Milky Way formed some time ago. And so all of these ones, yeah, have been disrupted. And like, so that's why we get like the present day one is like that.
Got it, thanks.
Yeah, so the other thing we can do, because we actually measured the rate of black holes as a function of redshift out to redshift 1, is we can try to ask, well, what is the formation rate of globular clusters as a function of redshift? And that's what's shown here in red. Here it's in terms of a number density, and here we've folded in that information about the mass distribution. It's in terms of a mass density. And then for comparison in blue is the star formation rate. And so one thing that we're measuring here is that the globular cluster formation rate, assuming that they're producing these binary black hole mergers, probably peaks earlier than the star formation rate at around a redshift of 3 or so, although there are very big error bars around this. And the other thing is that if you now integrate this formation rate and get a number density today, that number density that you'd infer is around 20 times higher than the density of survived clusters that we see in the galaxy, for example. So either that indicates that there's a lot of clusters that have a lot more clusters that have evaporated than those that we see, or that there are other environments that are contributing to that merger rate that I assigned entirely to globular clusters, which is very probable as well. Yeah, so I think this is also thinking about things evolving with redshift is a good transition to the next thing that I wanted to talk about, which is the merger histories. But I guess I can, if there are any other questions before I move on, I can take those as well. Okay, great. Okay, so yeah, we already had a little bit of thinking about this with thinking about globular clusters evolving with redshift, but more generally, the binary black hole merger rate that we observe follows the progenitor formation rate. So the progenitors of those black holes, whether they're stars in binaries like this or stars inside globular clusters, plus some delay time distribution, which is how long it took from the formation of those stars to the eventual merger of the black holes. And so that delay time distribution is dominated by the gravitational wave inspiral, right? So there's like a pretty short time between when the stars form and when the black holes are born, because these are massive stars, so they only live for like 10 million years. And then there can be a very long gravitational wave inspiral because gravitational radiation is so inefficient at shrinking this orbit. So that can take quite long. But yes, in general, the merger rate that we observe as a function of redshift depends both on the progenitor formation rate as a function of redshift and this distribution of delay times. And so the first thing, first little game we can play is if we know what the progenitor formation rate is as a function of redshift, we can infer the delay time distribution. So what I'm showing here is in blue is a little bit outdated at this point, but it's the measurement of the black hole merger rate as a function of redshift or look back time down here. And if you just want to consider the shape of that merger rate, so how much bigger is the merger rate at redshift 1 or 8 billion years ago compared to today, I've just normalized everything by the rates today, so it's easier to look just at the shape. And then in orange here is the star formation rate from the best fit from Maddow and Fragos. So if we assume that the progenitors of binary black holes follow this star formation rate, then the shape of the merger rate is telling us about the delay time distributions, because if the merger rate looks just like the star formation rate, then there's zero delay. If delay times are very long, then the merger rate is much shallower than the star formation rate. And so these other different lines are just different delay time distributions convolved with the star formation rate, varying the minimum delay time. And for this plot, I've just taken a flattened log distribution above this minimum delay time. But from here, you can already see that we're ruling out very long delay times because the merger rate that we're inferring is pretty steep. So consistent with the star formation rate and maybe even steeper than the star formation rate. One fun application of this is that if we learn something about the delay time distribution, we can use that in conjunction with learning about the host galaxies of these binary black holes. So this is something that people do a lot when thinking about like the host galaxies of short gamma ray bursts, for example. But we can try to use what we've learned about the delay time distribution from an analysis like this, and then ask what would it do to the host galaxy distribution of those mergers? So this plot is from a recent paper led by Aditya Vijay Kumar, who's a SETA fellow, and that it just shows that the stellar masses and the star formation rates that we then infer for the host galaxies of binary black hole mergers. The other thing we can do is now compare our inferred delay time distributions against theoretical predictions for the delay time distribution. So these are theoretical predictions from LICA that for different isolated binary evolution scenarios. So here is the common envelope evolution, where you have this, to me, magical common envelope phase that can just instantly shrink your orbit and give you very short delay times, versus if you don't have a common envelope and you're only evolving through stable mass transfer, where you have a shallower delay time distribution and less of a preference for the shortest delay times. So everything I showed before is assuming that we know that the progenitor formation rate of our binary black holes follow the star formation rate. But if we believe these models and we have a good prediction for what the delay time distribution should be, so here, like the total delay time distribution from isolated binary evolution looks something like a power law with a slope of -1 or a flattened log distribution. Then we can compare that to our measured merger rate and ask, what do we infer for the progenitor formation rate? And so that's what we're doing here. Is we now take that delay time distribution and we can measure the formation rate as a function of redshift, and that's shown here in blue. And then we can compare that to measurements of the star formation rate. So here's like a UV based measurement, and here's a UV plus reverse. Here's a UV and here's a UV plus IR measurement. And we can compare what we've now inferred for the progenitor formation rate to the star formation rate. And we infer that it probably, once again, like the globular cluster case, peaks at earlier redshifts than the star formation rate. And just concretely, if we divide these two things, so if we divide our inferred progenitor formation rate by the star formation rate, which here has been brought down by a factor of 10 to the -6 to make it fit on the plot, then we can measure the yield. So how many binary black holes do we have per unit of stellar mass as a function of redshift? And so for this delay time distribution with a power law slope of -1, then we infer that, again, the yield is higher at higher redshift. Okay, so one last thing. We expect, again, from Lika, she told me, that this yield depends on metallicity. So here's, again, this number of binary black hole mergers per unit of star formation stellar mass as a function of the metallicity. And there are some, there's a range of predictions, but we can use, say, this kind of average looking prediction here for what the yield does as a function of metallicity, and convert the yield that we measured as a function of redshift plus the yield that we've predicted as a function of metallicity into the metallicity distribution as a function of redshift. So focusing on this is that delay time distribution we've assumed with a slope of -1. And this green one here is, again, kind of assuming this average looking yield as a function of metallicity. And we can actually infer what these different assumptions plus gravitational wave observation implies for the average metallicity as a function of redshift. And that's shown here. So, if you make very different assumptions about what the yield is as a function of metallicity, then you can get these metallicity evolution with redshift that don't look right at all compared to these other measurements, which here are shown in this like dashed lines here.
Sorry, what exactly is yield here?
It's the number of binary black hole mergers that you get per star forming unit.
Okay, thanks.
Yes, so, okay, yeah, so, we can start to actually learn something about how metallicity evolves with redshift, for example, which is pretty fun. So yeah, the other thing that is kind of interesting to think about is from this model, what we're really doing is we're simultaneously inferring the merger redshifts and the formation redshifts of all of our binary black hole events. So you can actually ask, what does all of this imply for the formation redshifts of our actual events? Like, how long ago did the gravitational wave sources that we've observed form? And that's shown here in this plot as their merger redshift versus their formation redshift. And you can see that there's a lot of support here for binary black holes whose progenitor stars formed at very high redshift, like almost close to, like first billion years of the universe. So putting all of this together, we can actually infer that we've probably already observed binary black holes whose progenitors formed in the universe's first billion years. So even though all of the mergers happened in the last 8 billion years, because some of them probably experienced long delay times, then some of the stars actually formed within the first billion years of the universe, which is pretty cool given our current redshift reach. So yes, I think I just have a couple more things to say about hierarchical mergers, but does anyone have any questions so far? I see some thinking. Yeah.
So could you just go back to the metallicity yield plots for a second? Yeah. Oh, then sorry, next one. Yeah. So I just want to make sure I'm understanding. Are you saying, so basically the blue dashed line is what? Sorry.
The blue dashed line is what Maddow and Fragos say is the average metallicity as a function of redshift.
Okay.
This is just for comparison.
Okay, but that doesn't mean, so is it possible that there is some sort of metallicity bias in the progenitor systems such that what you're plotting doesn't actually have to track the observed metallicity evolution of the universe? I don't know if that's like a...
So I wouldn't say there's a bias. So it could be, okay, like say we've inferred, like we've used this assumption for the yield as a function of metallicity, and we've assumed like the delay time distribution that we've assumed, then those two things together imply that the average metallicity looks like this green line here.
Yeah.
And so if this is not actually the average metallicity as a function of redshift, then that could imply like this is this is not right. Like this yield as a function of metallicity, which came from the population synthesis models, is not the correct assumption, or the delay time distribution that we've assumed is not the correct delay time distribution. So you can view this as kind of like a self-consistency check on the tower of assumptions, or you can view it as a measurement of the metallicity as a function of redshift, depending on which assumptions you are confident in. Yeah, yes.
Hi. So I was wondering if you tried varying this Madal and Fragos model for the star formation rate, and if it has any impact on the results.
Yeah, so right. So I forgot to highlight that again in my answer to Savik, but the other thing that we've assumed is when we've measured this formation rate as the progenitor formation rate as a function of redshift to get the yield as a function of redshift, we've now divided it by the star formation rate. And here, for fun, I'm using a different star formation rate model, not the Madal and Fragos one, but it is consistent with that one. So yeah, that could also affect things because basically we were trying to disentangle the overall star formation rate from like a low metallicity tail of that star formation rate. So we're assuming that this green thing here is a measurement of some like effectively a low metallicity star formation rate. So which part of that you assign to the star formation rate being different versus the metallicity distribution being different is still degenerate. So that's not, yeah. So I think those assumptions won't change things more than like all of these different curves that you see here, which cover like every possible metallicity at every possible redshift. But yeah, that is an important part of it. Okay, cool. So yeah, I'll just go to the last thing, which is hierarchical mergers. Do black holes grow through repeated mergers? And so the question here is extremely simple. It's just, are the binary black holes that we're observing formed directly from stars? So when we observe a merger, are we observing a merger like this, where we have two first generation or 1G black holes that each formed from a star, and now they merge and we're observing the gravitational radiation, and then they form this other black hole, which is now a second generation black hole? Or are the black holes that we've observing actually a merger like this, where we had two second generation black holes that now merge again and form this even bigger black hole, or a second generation black hole merging with a first generation black hole? And so one reason that we want to answer this question is because hierarchical mergers are a very natural prediction of many of these dynamical environments that I talked about. So in particular, very dense environments with very high escape speed. So especially things like AGN disks or nuclear star clusters can, once the black holes merge, they stay in that dense environment, and so they can continue to go on and merge again, and we can get these hierarchical mergers. The other reason that we're interested in this question is because we've observed some very massive binary black holes in our sample. So in particular, if we look at our mass distribution, the merger rate as a function of that primary mass, then this does have a tail out to around 80 solar masses, where we've observed our most massive black hole system. So in terms of the actual rate, again, this is a log scale, so it's only around, it's less than 1% of mergers that involve black holes heavier than 50 solar masses, but that's still a non-zero rate. And we know that because we've seen them. And so for those very heavy black holes, you might think that it's very hard to form those from stars. And that's especially relevant because of pulsational or just pair instability supernovae, where you have this pair instability in the cores of your very massive stars, and that can lead to a gap in the black hole mass distribution in those 1G black hole mass distribution. So the black holes that came directly from stars, you might expect stars to not be able to make any black holes between around 50 and around 130 solar masses. And there's a lot of uncertainty on these numbers, which you can see because like the plot that I made here doesn't line up with what I wrote here. But basically there's some mass range, which is possibly forbidden to black hole remnants from stars. And so if we see black holes in this mass range, maybe the most natural explanation is that they just were formed from a previous merger of two black holes. Okay, so I am running out of time, so I might start to skip some details, but then you can ask me later. But basically, in addition to the black holes that are formed from a previous merger being more massive, they also tend to be spinning. So second generation black holes tend to spin at a dimensionless spin magnitude of around 0.7. And that's about the spin magnitude. What about the spin tilt? If we assume that hierarchical mergers are dynamically assembled, then the spin tilts are randomly oriented. This is huge caveat around this because I don't want to make Savik very mad at me. This does not apply to AGN disks, so don't take any of these conclusions to hold to AGN disks. But anyway, these two things together will imply that a fixed fraction of hierarchical mergers will have large misaligned spins. And so I'll just show kind of one summary plot of this result, which is we can actually, just measure what is the fraction of binary black holes with these moderately large misaligned spins. And I'm skipping over like why I picked negative 0.3 here. But basically, this fraction of binaries with large misaligned spins, we can convert that into a fraction of hierarchical mergers. And we can take that as a function of the primary mass of the black hole, because we might expect hierarchical mergers to account for a larger fraction of the population at higher masses compared to low masses. And that is what we see in the data, and that at low masses, we can constrain that there are essentially no systems with large misaligned spins. So the hierarchical merger fraction down here is very small. But as we go out to higher masses, it is now possible. It's not required by the data, but the data is okay with having more misaligned large-ish spins at those higher masses. And so the hierarchical merger fraction can increase with mass. So by the time you get to around 60 solar masses, it's possible that all of those black holes are hierarchical merger remnants. Thanks. But that does not seem to be the case down here because we simply don't have enough spinning black holes, and in particular black holes where the spins are misaligned with the orbit. Okay, and then just as a last slide here, one thing that we can start to ask is like, if stellar mass black holes do merge with each other and build up heavier black holes, can this somehow tell us something about supermassive black holes? And we don't really have enough information to tell you that. But what my student Ariana recently did, so this I think was on arXiv just this week, is did a model where we compared the merger rate in binary black holes that we actually observe here at these low redshift, assume that the progenitors follow the star formation rate with some metallicity dependence and some delay time model, and fit that to the low redshift data, which here redshift is going this way. So universe is getting older this way. And if we extrapolate that back to the beginning of the universe, we can have this guess of how much mass is in stellar mass binary black hole mergers at very early times. We can start to compare that maybe to the mass in supermassive black holes, which is shown here in green, just taken from an empirical model from Trinity. And so you can see that, maybe in the first billion years, the mass in stellar mass black holes is higher than the mass in supermassive black holes. Exactly what you make of that is, again, we don't know. We just looked up the mass. So whether you can actually get stellar mass black holes contributing to the seeds of supermassive black holes is beyond this analysis, but again, just an interesting thing to think about. Okay, so just to conclude, hopefully I've convinced you that there's a lot that we can learn from gravitational wave populations of stellar mass binary black holes. So I didn't talk about all of this, but I'm just going to put a bunch of words up so you can ask me about them later if you want. So one, how are black holes and neutron stars made? Thinking about things like supernova physics and the parent stability physics. I didn't talk about a mass gap between neutron stars and black holes, but that's also interesting. How do neutron stars and black holes get their spins? How do they form and find their merger partners? And then stepping out from like individual binaries and thinking about the cosmic history of this population. So how does the population evolve across cosmic time? What can we learn about metallicity, globular clusters, star formation rate? What can we learn about the host galaxies? And then what are the cosmological implications, which I didn't talk about at all, but there's a lot of very interesting work being done also by a lot of people here about things like measuring the Hubble constant, probing dark energy, and then learning about the large scale structure and like lensing of gravitational waves. So yeah, with that, I will stop talking and happy to take additional questions.
Right. Thank you, Maya, for that great tour of GW populations. Do we have time maybe for one question? Anyone dying to ask Maya for? Yeah.
Okay. Well, that's a question Billy asked. I've already asked a lot, right? So O4 has a lot more events, but also like you could still restrict your number of events to 90 and just use the brightest ones and have better measurements. Is there some parameter beyond CAIAF that will become more available for this type of study? Like, is there more information with harnessing the noise?
Yeah, as far as spins, yes, there is more information in the data if we have good enough waveform models to reliably extract it. So we already do have inference from like observing precession, for example. So like kind of like so chi effective affects the frequency evolution. There's like an effective spin precession parameter that affects the amplitude modulations that we can start to tease out. Beyond that, there also is information because of things like the recoil kicks that gravitational waves get about, for example, the azimuthal angle. So if I can go back to this picture, like here, like if you project these spins into the orbital plane and like measure the angle between the spins vectors and the orbital plane, that also like affects things like the recoil kick that the binary receives. And that can actually be really interesting for like inferring, which black hole like which spin started off aligned versus which one didn't, which can inform things like supernova kicks. And again, yeah, so like VJ and Max and people have worked on measuring that angle, like with like numerical relativity surrogate waveforms.